Question number 7 on the Unit 1 test review. So in this one class, they're giving us a pattern, and we also need to figure out, is this linear, exponential, or quadratic? So let's take a look at this, see if we can find evidence. One of the easiest ways to do this, or easier ways to do this, is actually count the number of squares that are in each one. So let's go ahead and do that. We got 2 here. We've got 4, 5, 6 here. There's 9, 10, 11, 12 here. And when you look at our rate of change, we're going to add 4 to get to 6. And from 6 to 12, we have to add 6. So you clearly can see it's not a linear pattern. So it can be exponential or it could be quadratic. But exponential also doesn't make sense if you think about this. 2 times 3 will get you to 6, but 6 times 3 gets you to 18. So it's not actually predicting the next figure 3 after figure 2. So it can't be exponential, so now we know it's quadratic. So just by looking at the rate of change here, we can actually write this is clearly a quadratic. So you can either use the pattern to figure out the quadratic equation, and I would tell you I would much rather do that. I think it'd be relatively quick if we did it that way. The other way you could do it is you can make a table and you can find the quadratic equation just like we did in question number 6 and question number 4. So let's go ahead and fill out our table. For figure 1, we've got 2 squares. For figure 2, we have 6 squares. And for figure 3, we have 12 squares. And we can see, class, if we check our first difference, we already saw it a moment ago. We're adding 4 to get from 2 to 6 and adding 6 to get from 6 to 12. And remember, class, if we know this is quadratic, then we know the first difference or the rate of change has to be linear. So if we added 4 on our first figure to get to 6 and 6 on our second figure to get to 12, then we absolutely need to add 8 to get to our next figure. And that's going to be 20. And then we're going to add 10 to get to our next figure, which is 30. So we can predict those things because we decided that it was quadratic, figured out it was quadratic, and therefore we know, class, for quadratic equations, the first difference is always going to be a constant pattern. And now we can see how this plays out. From 4 to 6, we have to add 2 to get from 4 to 6, add 2 to get from 6 to 8, and add 2 to get from 8 to 10. So I can use this table the same way we found the quadratic equation in questions 4 and 6. So I can show you that same process, but you've already seen that. Let's go ahead and go the other route and look at the pattern. So on the pattern, we know that the figure number is right here, 1, 2, and 3. And typically on patterns, we're going to take the figure number and say, okay, that's actually going to be representing the variable n. So n equals 1 here, n equals 2 here, and n equals 3 here. And if you've been paying attention to looking for quadratic patterns, you're looking for the largest rectangle or the largest square. And I usually look at the highest figure first. It's really hard to tell what to do because this is actually a rectangle. You'd think, oh, I'm going to use that rectangle. But you're not going to see that rectangle growing in a consistent pattern from figure 1 to 2 and 2 to 3. So if I look at this first one, class, I can see right here, it looks like I've got this big old square right here. And if I look at the next pattern, I can see, well, I got the same square here. It's a little bit smaller than the other one. Sorry, I'm losing my voice a little bit. I apologize for that. And that means this becomes the square we're comparing it to right here. In class, if you look at that square in each of these, take a look at the dimensions of that. This square is 3 wide by 3 tall, but that's our n value. So we can represent that as n by n. And this square turns out to be the same thing. It's 2 by 2, 2 wide by 2 high, and that's my figure number. You're looking, class, for some way that you can write the dimensions of this square, or it could be a rectangle as well. In different patterns, it could be a rectangle. You're looking for a way to write that so that when you substitute the n value in here, you actually get your dimensions, and it has to be consistent. This is an n by n square. This is an n by n square. And doggone it, same one over here. This square right here is n by n. So the first thing we see in our explicit function, we're going to go ahead and write, usually we do these, we can just write f of n. That's typical. It's not telling us which function letter to use. So f of n equals n times n. There's our length times width. Our length times width of this square right here. And that means, class, this equation right here already figures out these squares. If you think about this, if we plug in 3 times 3 is 9. There's 9 squares there. If you plug in n equals 2, 2 times 2 is 4. There's our 4 squares. And if you plug in n equals 1, 1 times 1 is, there's 1 squared. So now we've got our equation started. It's very much like question number 4 and 6. We started our equation. Now the question is, does this predict the number of tiles in each figure? And the answer is no. It predicts the number of tiles in each of these squares, but we've got leftovers here. And if you look at this, we have 3 leftovers here. We've got 2 leftovers here, and we have 1 left over here. Well, good news, class. N actually predicts the number of leftover tiles that haven't been counted. This is n number. N tiles, and n tiles. So we've got n times n, and we're going to add another n to that. You don't multiply. You're not multiplying this. You're just saying, I've got n tiles left over. That's 3 left over. I've got 2 tiles left over here. That's n equals 2. That's equal to n. And we got 1 tile left over here, and that's equal to figure 1, or n equals 1. And now we're going to go ahead and simplify this. So we've got f of n equals n times n is n squared. And all we have left over is plus n. Let's check this and see if this works. So here's our check step. Let's plug in 5. If we plug in 5, we should get 30. So f of n, which is f of 5, equals 5 squared plus 5. Well, that's equal to 25 plus 5, which is actually 30. That's exactly what we wanted to predict when we plugged in the figure number 5. We'll have 30 tiles. So there's a way to write our explicit function. I'll go ahead and circle that. Now I will tell you, if you follow the same strategy for questions 4 and 6 using the table alone, you're going to get the exact same equation. It may not look the same to begin with, but when you simplify it, it will be the exact same equation. It's the only equation that actually predicts the right number of tiles for every figure you see in the diagram and for the 2 extra figures that we put on our table. Last thing, classes, let's graph this. This should not be a big issue for you. Take a look at this. For figure 1, we're at 2. Well, this is 5 and this is 10. 2 is going to be somewhere around here. For 2, we've got 6. That's right above 5. For 3, we have 12. That's 2 above 10, so right there. For 4, we have 20, which is right here. And for 5, we have 30, which is right here. Class, you put a ruler on that, you'll realize that's not a straight line. It can't be a straight line, a real straight line, because that would be a linear equation. This is quadratic. But class, because we have figure numbers, we're not going to figure out figure number 1.2 or 1.5. So because we only are looking at whole numbers here, that means this graph is going to be discrete. So I'm just going to make a note here. It will be discrete because it is actually just finding points. It's not finding all the spaces or values inside of those points, so they will not be connected. There is question number 7, how to find the equation, in this case using pattern recognition, or finding squares or rectangles that we can represent with the figure number n, and then just figure out what the leftovers are, and those show up right here. Again, if you look at the consistency between that and these questions up here, take a look at number 6. If we look at this, we figured out n squared, and then we had to figure out what our leftovers were. This process right here, class, finding the linear number of tiles that are left over, or in this case, we counted too many, so we have to actually remove some of those from the equation. And there's where we removed 5. All right, there's end of question number 7. I'll bring it back over here so it ends on the picture. All right.